Hey everyone, and welcome back. This is part 2 of our mini-series all about reliability, the ultimate quality check that tells us if our psychological tests and measures are actually consistent and trustworthy. In part 1, we set the stage by covering the core ideas such as the classical test theory, the ratio of true variance to total variance, and the nature and sources of error. If you want to see that video, check it out linked in the card up there. And now let's pick up where we last left off. Since we now know where error comes from, our next step is to use statistical methods, specifically the classical reliability methods, to measure exactly how much error exists in a test score. So classical reliability methods are methods to determine a test's reliability coefficient, which is just a way of quantifying or putting a number to consistency. So to find this number, they undergo multiple different methods and ultimately calculate a correlation. A high correlation, which is basically a number close to 1, means the test is consistent. And as it further goes away from 1, the less consistent it is. So let's dive into the first way researchers check for consistency. This is the test-retest reliability. This is all about making sure a test score is stable over time. So the whole point of test-retest reliability is to target time sampling error. We want to know, if we measure a stable trait today, will we get basically the same result if we measure it again later? If not, the test is unreliable because the score is too affected by the time between the two test sessions. If you notice, I mentioned stable traits, not just any trait. This is because this method is perfect for measuring static or stable characteristics, because these are traits that are supposed to be enduring and relatively unchanging regardless of time, like your core personality or your general IQ. So this means you do not use test-retest reliability when measuring the opposite, which are dynamic traits which change quickly over time. But the main concern with this method is setting the right time interval. If the break is too short, you run into carryover effects. The test takers might literally remember the questions or the answers they gave the first time, or maybe they have the opportunity to think about the test in the meantime in between the two sessions. And so this memory or practice artificially inflates the second score, making the test look more reliable than it actually is. So how does this method work? This is one of the more straightforward methods that we will discuss. First, you give the exact same test to the same group of people. Then you introduce a time interval. It could be a few weeks or often several months, like 6 months. There is no one perfect time interval, so it depends on the context of what you're measuring. Then after the time interval, you will give the same exact test to the same exact group of people again. You will then calculate the correlation between the first score and the second score, how stable the scores are between the time interval. So now let's go over a real-life example of this. Let us imagine a financial researcher who develops a new scale to measure risk tolerance. This is basically how much risk an investor is comfortable with, and this is a core trait that shouldn't change overnight. And so, the researcher gives the risk tolerance test to 400 financial investors in January. They then give the same exact test to the same 400 investors in July. They calculate the correlation, which says around 0.85, which is a strong correlation. This confirms that the scale is reliable. It proves that the trait that the test is measuring is stable. And so the investors who were risk-tolerant in January were still risk-tolerant 6 months later. Next up, we have parallel and alternate forms reliability. This method tackles the problem of item sampling or test construction error. It does this by making sure that the specific questions chosen for the test aren't what makes the score reliable or unreliable. So this method primarily targets item sampling error, and actually also time sampling error if you wait between forms. So the goal is to prove that the two different sets of questions, basically Form A and Form B, are measuring the exact same thing with the same consistency. So in the name itself, parallel and alternate forms, this means that in a specific test, there are at least two different forms, as mentioned, usually Form A and Form B. And as you have also possibly noticed in the title, there are two types of forms, parallel and alternate. While they are similar, they are not exactly the same, so let's differentiate them. So let's start with how parallel forms work. Parallel forms represent the most rigorous standard of equivalence. They are designed to be statistically interchangeable, like two perfect clone twins. So both Form A and Form B must be identical in content, format, difficulty, and variance. So for two forms to be truly parallel, they must have equal means, which means the average score on Form A must be equal to the average score on Form B, and also have equal error variances, which means the amount of random error in Form A must be the same as the error in Form B. The correlation between the two forms is calculated, yielding the coefficient of equivalence. If the forms meet the strict criteria, the researcher can use them interchangeably without worry. Now, what about alternate forms? Alternate forms is the term used more frequently in practice because it has slightly looser or less strict requirements for statistical equality, basically making it easier to achieve. So these forms are still built to be equivalent in terms of content and difficulty, and they are used for the same purpose as parallel forms. However, they are not as strict as parallel forms wherein they do not need to have equal means or error variances. And so similarly as with parallel forms, the correlation between Form A and Form B provides the coefficient of equivalence, proving that the scores are consistent despite different questions chosen. So now let's go over a real-life example of this. So, as mentioned, this is one of the most rigorous and best methods for minimizing issues, such as remembering answers or cheating. So imagine the Certified Public Accountant Licensing Board. They need to administer a major exam on the same day in two testing sessions, basically one in the morning and one in the afternoon. So they decide to use alternate forms, where they use Form A in the morning and Form B in the afternoon. They do this so that if a morning taker leaks specific questions, Form B prevents that information from compromising the afternoon session scores, as the afternoon test has different items. So to ensure this method is valid, the board must prove that the specific items selected for Form A versus Form B did not unfairly advantage or disadvantage any group. So they do this by demonstrating a high coefficient of equivalence before the examination. If the correlation is high, it means someone who scored high on Form A would also score high on Form B, since the two tests are functionally identical. Now let's move on to inter-item consistency. This is probably the most frequently used method in research today because it is very efficient. Why? Because it requires only one test administration. It tells you whether all questions on your test are truly working together to measure the same thing. So this one has many methods, so this is probably our most comprehensive section. So this method directly focuses on homogeneity or homogeneity. So this is the ideal state where all items on your test are measuring a single specific trait or factor. For example, a test is only measuring anxiety, not a mix of anxiety and depression. So this would mean that heterogeneity is the opposite, where your test items are measuring more than one factor, making the total score of what you're trying to measure a bit muddy and inconsistent. Why? Because you are measuring different things that you are not acknowledging during the test construction process. You thought you were just measuring anxiety, but you were measuring anxiety plus some other stuff. So basically, the higher the inter-item consistency or internal consistency, the more homogeneous your test is. So how does this work? Unlike the methods we covered, it looks at the mathematical relationship between every single item on the test. So first, the test is given once to a group of people. You mathematically compare every single item to every other item and to the total score. The resulting reliability coefficient is most commonly calculated using Cronbach's alpha or Kuder-Richardson 20, and these formulas provide the average of all possible split half correlations. So basically the average of the comparison between every single item to every other item and also to the total score. So this is a very comprehensive method, which results to a far more robust estimate of internal consistency. We will discuss these alphas and Kuder-Richardson 20s later on in the next part. But basically, inter-item consistency is the go-to method for measures of dynamic characteristics. So this is the opposite of stable traits that we talked about earlier. These are less stable and can change quickly. So this includes mood, state anxiety, and current job satisfaction. So if we look at it in another way, since these traits fluctuate, using test-retest reliability wouldn't make sense, because a change in score might just be a normal change in that less stable trait, like a change in mood, which isn't a reflection that the test is unreliable. So let's go over a real-life example to visualize this better. So imagine a human resources department wants to measure employee engagement with a 12-item survey taken at the end of the year. Since engagement can fluctuate based on recent events, they only administer the test once. So the survey includes items like, I feel motivated to come to work. I often think about leaving my job, which is actually reverse scored. And I understand how my work contributes to the company's success. And so the researcher then calculates, let's say, the Cronbach's alpha for all of the 12 items and gets an alpha of 0.88. So this is an exceptionally high value, which confirms that all 12 questions are consistently measuring the same underlying construct, which, as mentioned, was employee engagement. So this means an employee who strongly agrees with item 1 is highly likely to strongly agree with the sentiments of item 2 and 3 and so on, assuming that they are not reverse scored. So if they had found a low alpha, it would signal that some items are actually measuring a different trait, thus requiring revision. So, as mentioned, there are a variety of methods to calculate internal consistency statistics, each with its own strengths and weaknesses. So let's go over each one. First, we have split half reliability. So split half reliability is a popular and efficient way to check a test's internal consistency, basically treating one test you gave once as if it were two separate mini-tests. So how does this work? The whole point here is to see if the questions in the first half of your test are measuring the same exact thing as the questions in the second half. So the great news is you only have to give the full-length test to your group once. This saves time and avoids problems associated with making people take the test again later. So we need to divide the total test items into two scoring groups that are truly equivalent. So you can't just take the first 20 questions and the last 20 questions, because the person might be tired, warmed up, or distracted by the time that they get to the end. So the most common technique is the odd-even split. You calculate one score using all the odd-numbered items, such as 1, 3, 5, and so on, and the second score using all of the even-numbered items, such as 2, 4, 6, and so on. This ensures both halves get an equal mix of early and late questions, thereby ideally evening out things like fatigue or confusion. So once you have two scores for every person, so one odd score and one even score, you calculate the correlation coefficient between them. That value is the reliability of your half-length test. So here's the little tricky part about this. So the correlation you just calculated is an underestimate of your full test reliability. Why? Well, if you think about it, if you shorten a measuring tool, it generally becomes less dependable. We know that longer tests are naturally more reliable than shorter tests, assuming that the quality stays the same. So by cutting your test in half, you artificially lowered its reliability score. So to fix this, we use the Spearman-Brown prophecy formula. It is a statistical tool used to extrapolate the score back to the original length. It basically steps up or increases the observed half-test correlation to predict what the reliability would have been for the entire full test. So the resulting corrected number is the final reported reliability for your entire test. So let's have a real-life example scenario. So let's say a researcher uses a 40-item survey designed to measure employee burnout. So the researcher splits the 40 items into 2 item halves, consisting of odd and even, and finds that the correlation between those halves is 60. So 60 alone is a, let's say, okay but not great result. But again, remember, this is only an underestimate. So they plug that 60 into the Spearman-Brown formula, and the formula estimates the full 40-item test reliability to actually be 0.75, which is a pretty okay reliability score. So this 0.75 is the proof that the questions in the first half of the test are similar to the questions in the second half in terms of reliability, confirming the scale's good internal consistency. So now let's discuss the Kuder-Richardson formulas, more notably known as 𝗂𝑟20 and 𝗂𝑟21. These are specialized calculations that assess inter-item consistency for a very specific type of test item, the kind with a simple right or wrong answer. So basically, the 𝗂𝑟 formulas are used typically for dichotomous test items. This means the test items are answered with only one right answer. There are no partial points or subjective scores. So for example, a correct or incorrect item, which is usually scored as 1 or 0. So if your test involves rating scales such as the 1 to 5 strongly agree scale, you're better off using Cronbach's alpha instead, which we will describe later on. So as you've noticed, there is 𝗂𝑟20 and 𝗂𝑟21. Both formulas use internal consistency for dichotomous items, but they differ in how much detailed information they use. So 𝗂𝑟20 is a more accurate formula because it accounts for the variability of difficulty of every single item. So it basically takes into account how each single item could be different in terms of how hard or difficult they are. So if some questions were much easier or much harder than others, 𝗂𝑟20 factors that into the final reliability estimate, making it a robust measure. Meanwhile, 𝗂𝑟20 is a quicker, simpler calculation that assumes the assumption that all test items have equal difficulty. Because this assumption is rarely perfectly met in real-world tests, 𝗂𝑟21 generally yields a lower, more conservative estimate of reliability than 𝗂𝑟20. And due to modern computing power, researchers today almost always prefer 𝗂𝑟20. So how does this work? Imagine a school administers a 50-question multiple-choice math assessment. So every question is scored 1 for correct and 0 for incorrect. So a researcher uses the 𝗂𝑟20 formula to calculate the reliability. If the 𝗂𝑟20 value is high, such as 0.85, it proves the test has strong inter-item consistency. This means a student who got question 5 right would also likely to get questions 15 and 30 right. It confirms that all 50 items are consistently measuring the same underlying math skill, and the scores aren't just a mix of who got lucky on which random question. Now let's move forward to Cronbach's coefficient alpha, which is also known as just alpha. It is the most widely used statistic for assessing inter-item consistency today. It is essentially like the reliability holy grail because it can handle almost any type of score. So alpha is essential for polytomous test items, though it can be used for dichotomous items as well. This means the test items have 3 or more alternative responses that yield different scores. These are the items where people can express different degrees of agreement or frequency, and not just a simple right or wrong. For example, the Likert scale, which is a 5-point scale from strongly disagree to strongly agree. And so because most personality, attitude, and social science surveys use these rating scales, alpha is the default standard for proving their consistency. So alpha is calculated after just one administration of the test. You can think of Cronbach's alpha as the reliability method that gives you the best possible answer. When you use the split half method, for example, you only test consistency using one pairing, like odd versus even. But what if dividing the test into the first 10 questions versus the last 10 questions would give a totally different correlation? So which result would be the true reliability? So conceptually, alpha solves this problem by running a massive statistical calculation that is basically equivalent to splitting your test into 2 halves of every single way imaginable, like an infinity cake, for instance. So like think of an infinity cake where you can split them into multiple different halves to pair them with each other. Then you calculate the correlation for each and every one of those pairings. Then, taking the average of all of those thousands of possible split half correlations, this average result, which is the Cronbach's alpha, now becomes a much more robust and stable measure of your test's internal consistency than any single split half correlation could ever be. It gives you confidence that your items are cohesive regardless of how you divide the test. So a high alpha, which is usually between 0.70 to 0.90, means that the item set is very cohesive. All the items are contributing equally and consistently to the measurement of a single trait. So now let's go over a real-life example to better visualize this. So imagine a manager wants to use a 10-item teamwork evaluation survey where subordinates rate their peers on a scale of 1 to 7. The manager then administers that survey once and calculates the alpha, which comes out to 0.94. So this is a very exceptionally high alpha, which confirms all 10 items are measuring the same single underlying construct consistently. So if a peer scores high on one item, they are highly likely to score high on all the others, proving that the measurement is reliable. Now let's discuss the final main method of checking classical reliability, inter-rater reliability. So this method tackles the error introduced when human judgment is involved in the scoring process. So the core purpose of this is to ensure that the scoring is consistent, not between tests or items, but between different people who are scoring or observing the results. So this is basically the degree of agreement or consistency between 2 or more scorers or observers regarding a particular measure. If 2 different judges look at the same essay, performance, or behavior, they should assign highly similar scores. This is crucial for any scoring process involving subjectivity. This includes evaluating job interviews, observing behaviors in a classroom, or grading essays and artistic performances. So when scoring involves a categorical scale, which means the judges are placing an observation into specific categories or types, like low, medium, or high, rather than just assigning a continuous score, which is a number, you have to use certain specific statistical tools. This includes Cohen's kappa, which is used when you have exactly 2 raters scoring the same thing, and as well as Flee's kappa, which is used when you have 3 or more raters scoring the same thing. And there are many other kappas as well, but these are the basics. So these coefficients measure the agreement between raters while also correcting for the level of agreement that might have happened simply by random chance. So let's go over a real-life example to better visualize this. Imagine a competitive graduate school admissions committee with 3 members. They are independently scoring incoming application essays. So each of the 3 members reads the same essay and assigns it a category. So it is either a top tier, mid-range, or unsuitable. And so the committee calculates Flee's kappa on all their scores to see how much they agree. So a low value would immediately signal a problem. It means the scoring is unreliable because the judges can't agree. This typically indicates that the scoring rubric is too vague, such as, for example, if they are trying to rate on creativity, the word creativity itself is undefined on their scoring criteria. This could also possibly mean that the raters need additional training in order to standardize their interpretation of the criteria. And that's our complete mastery guide to psychometric reliability basics. I know this didn't cover everything, but just the basics. But hopefully it helped you master it to form a foundation moving forward in your other studies. If this guide helped you master these concepts, please hit the like button. It truly helps the channel. Subscribe for more lessons like this, and thanks for watching. I hope to see you next time. Bye bye!